Hi everybody. Big day in your geometry class today. This is the first lesson in the whole unit about right triangles. Day one with right triangles. And today we're going to take up the topic of geometric means. And it might be that you don't know a lot about geometric means, but actually if you did today's attendance check, you figured out something about a geometric mean already. I think on the attendance check I asked you this question. What single number can fill both of the means positions with extremes of 5 and 20? And if you wrote a proportion like this and put the extremes to be 5 and 20, and say, well, what single number could fill both of those positions? You might have done it like this. I put an x here and an x there. Since it's the same number filling both of those positions, it would make sense to me that x squared would have to equal whatever this product is, and that's 100. I'm going to take a square root of both sides quickly and easily. X would have been 10. That's the square root of 100. So I'm thinking, well, 5 is to 10 as 10 is to 20. Yeah, that's a half and that's a half. So 10 does fill both of the means position with extremes of 5 and 20. But what's important about that truly is 10 is the geometric mean between 5 and 20. Whenever you have the same length or the same number in both of the means position between a pair of extremes, you've got what's called a geometric mean. We're going to find some geometric means here. Let's get going down that path. Study the triangle at right, this right triangle. And it has to be about the legs. And just to get the nomenclature in place, AC is a leg. The two segments that are adjacent to the right angle are the legs. And BC is a leg. Could have called it CB, that's the same. And the hypotenuse is the side that's opposite the right angle, the largest side in the right triangle. That's going to be AB. And then it starts to get interesting. Show the altitude to the hypotenuse of the right triangle. What you have to remember, for it to be an altitude, it must be perpendicular to the line of the opposite side. That'll be easy enough to do. I'll go from C to the line of the opposite side as perpendicularly as I could, show that those are right angles, and call that place X. So I just built the altitude from to the hypotenuse of the right triangle, and I called it CX. The two smaller right triangles are similar to the large right triangle, and we're going to complete some similarity statements. But to complete those similarity statements, we really need to discuss some angles. Let me call this one right here angle 1, and this one just angle A. Would you agree that angle 1 and angle A are not congruent, but in fact, because they exist in this right triangle with a 90 here, that those two would add up to 90? Therefore, angle 1 and angle A are complementary. But looking down that same path, what about angle 1 and angle 2? Are they also complementary? Don't they also add up to 90? They must. And interestingly, something from the first semester, if two angles are complements of the same angle, then those two angles are congruent. So the angle that I've labeled as 2 has to be congruent to this angle at A. A little further down that same path, thinking about this triangle on the right-hand side with a right angle at X, isn't it true that the angle at B and the angle at 2 are also complementary? If 90 went there, those two would have 90 to share. So that forces angle B to be the complement of angle 2, and angle 1 was the complement of angle 2. So I know now that angle B and angle 1 are congruent. So I ought to make those marks in that triangle. Now I know lots of things about congruent angles, and I can probably make clever similarity statements. Let's start down that path. And when I say triangle ABC, that's the big triangle. And I know that triangle ABC is supposed to be similar to this small triangle on the left. Let me give you a little display about this. Now's probably a good time to do that. So I built a right triangle, just out of construction paper. Let me just show you a couple of things about it. There's a right triangle and an altitude drawn to the hypotenuse. And I want to think about these triangles that lie inside of it, like this one and this one. So we really have a sketch pretty much like the other one, just a right triangle with a right angle up here and an altitude drawn to the hypotenuse. And I'm here to say that all these triangles, this pink one and this blue one and this yellow one, are similar to each other. And it's not altogether obvious that that's true, but if I do this, let me just play with it for a moment. display them in this orientation, I think anybody looking would say, yeah, those are similar triangles, aren't they? In fact, now I'd have parallel lines here. If we turn them in this way, just trying to observe this, you think those triangles are similar to each other? Corresponding angles are congruent? Yes, they are. And their sides are in proportion. So, I'm going to put those aside and get back here and pay attention to these details. I'm going to name similar triangles. And ABC being the big triangle, I'm going to name the smaller triangle on the left. The angle at A matches the angle at A. That's in both of those triangles. And the angle at B in the big triangle matches this angle at C in the smaller one. So I start with AC. And the C is the right angle in the big triangle, so the right angle in the smaller triangle is X. So there's my similarity statement. Talking about the small triangle being similar to the large one. But the other small triangle on the right is also similar to the large one. I start off with ABC in the same order. In the right-hand triangle, what angle is the same as angle A? Well, that angle with two slashes matches this angle, doesn't it? So I have to start with C. And B in the right triangle, the big right triangle matches B in the smaller right triangle on the right, so that's going to stay B. That's just congruent to itself by the reflexive property. And ABC with a right angle at C forces to go with CBX. I'm just paying attention to the angles being in the same positions. But now, watch this. The two smaller right triangles, they're both similar to the big one. That forces them to be similar to each other. And I want to make that similarity statement here. But it'll be easy because these two triangles are similar to the same triangle in the same order. So I could just name it that way, triangle ACX, and not pay attention much to angles. It's got to be similar to triangle CBX. I'm sure that that's truthful. If you walked through and found those angles, they would be congruent as well. The reason we care about these similar triangles, why would we care, why would we make such a fuss, is they give us geometric means. That's a big deal. And here we're going to go, we'll start writing some geometric means. To do this, I'm going to use the first case first, this situation. I'm going to give you a side from the first triangle, and you'll have to figure what side goes with it. Let me start off by saying AX. AX on this triangle corresponds to somebody on the other. That'd have to be AC, wouldn't it? Now come back to this right-hand triangle, and let me use AC. You see what's going on here? I got AC in both of the means positions, and that's going to make it be a geometric mean, but stay with me here. AX went with AC, the way that AC, first and second, goes with AB, first and second. That's our first set of geometric means. This is something we're going to have to memorize, but I got a way to memorize it, so just stick around and it's going to be okay. We're going to write another set of a proportion here. This time it's going to deal with the second set of similar triangles. The triangle CBX is similar to the big one. We've got to name them carefully. Let me take a side from the first triangle, AB. And AB, you would say, corresponds with CB. But since I want to get the same thing in both of the means positions, AB is the CB. Come back here and give me CB again. And CB corresponds with XB. Lo and behold, CB is a geometric mean between these two lengths. We're going to study those and look at this figure and find a way to memorize that in a moment. Something that works for me, and if it doesn't work for you, you got to find another way to memorize it. But I got a way that works for me. One more time. I'm going to use these similar triangles this time and write another proportion, and I expect to get a geometric mean, the same thing in both of the means positions. From the first triangle, let's take AX. Who does AX have to go with? You'd have to say CX, wouldn't you? First and third position. And because we want the same thing in both of the means position, let's go back to CX up here again. As CX, second and third, goes with BX. There's another geometric mean. Now, memorizing these won't be very helpful because the triangle might not always be called triangle ABC. But let me make some sketches, and you watch this very closely, and I think it'll be very useful for you. It says here first, AC is the geometric mean between somebody and somebody else. And that goes right from this one right here. AC is the geometric mean between AX and AB, between those two links. I would like to make a sketch that shows me how to memorize that. It's not going to be, too simple, but it is quite workable. I'm going to think about this picture, and it tells me AC. Let me back up a little bit so you can get a good look at this whole page. AC is the geometric mean between AX and AB. AC is the geometric mean between AX and AB. Since this was the geometric mean, AC was, I'm going to put 2 slashes there, and it was the geometric mean between AX and AB, between this length and the full length. This will be a helpful sketch to me. The one with 2 bars is the geometric mean between these 2 lengths, the short one and the full length there. Now that's a bothersome thing. Stick around, it's going to get easier. BC is the geometric mean, it tells me here. And we're set up to see that in fact it is. BC and CB are the same guy. So BC is the geometric mean between AB and XB. That's something I got to remember to use to solve other questions. I'm going to make a sketch like it and refer to this diagram up here. Same kind of a triangle, a right triangle with altitude drawn to the hypotenuse. But look at this, BC is the geometric mean between AB and XB. BC, this length, is the geometric mean between BX and AB. So I'm going to make this sketch. This segment is the geometric mean between its part of the hypotenuse and the full hypotenuse. That's easier than remembering short side of this one is the short side of that one is hypotenuse is the hypotenuse, if you can memorize this sketch. Either way works, but I'm liking that sketch. It works very well for this diagram. One more time, let's see if we can't figure out where this would go. Is XC a geometric mean? Sure, XC, CX, XC is a geometric mean between AX and BX. What kind of sketch would help me to memorize that? Well, I'm just going to sketch that right triangle with an altitude drawn to the hypotenuse. And this tells me that XC, that's the guy up and down in the middle, is the geometric mean between AX and XB, between the 2 parts of the hypotenuse. So I'm going to put 2 marks on this guy, one on either side, and say it's a geometric mean between the 2 parts of the hypotenuse. It may not be terribly helpful yet, but these have been very helpful for me. This is how I memorize this stuff. I'm going to work this first question right here, but it's going to require that I use another piece of paper. I'm going to pause. So, just so I can work that last question with a little space so I can talk about it, I've sketched that same figure, and I'm going to find this length, and that one. I'm going to call them X, Y, and Z, just so we can talk about them quickly and easily. But I'm just working the last question from this page. I also made those 3 sketches so I can sort of show you how I remember them, how this goes. I got to find this value X. Is X a geometric mean? In this position, yeah, this guy is a geometric mean, isn't it? Because it shows twice. It's going to show twice in the proportion. X is a geometric mean. And you would have to think X is a geometric mean between this segment, 4, and the full hypotenuse, which is 16. And that's the way you could get that value for X. Now, you could be thinking other stuff. You could go through all of this. This small triangle is similar to the big triangle, and the short side of the small triangle is to the short side of the big triangle, as the hypotenuse of the small triangle is to the hypotenuse of the big triangle. that's really going to give you the same proportion. If you memorize this, that would work, or you can compare sides. But I get x squared equals 64. So I think that x would have been 8. This length would have been 8. And on my problem, that would have been segment AB is 8. This was triangle A, B, C, and D there. Then I'm going to find x and y and z. I've got x. I'm going to go for y. I ask you first, is y a geometric mean? In fact, it is. This vertical segment in the middle, because these two triangles are similar, here's what I'm really going to depend on. This vertical segment with 2 bars on it is the geometric mean between the 2 lengths of the hypotenuse. That's right of proportion. This vertical segment is the geometric mean. I can put it both of the means positions between the 2 parts of the hypotenuse, between 4 and 12. And that really comes from, since these 2 triangles are similar, the short side of this one is to the short side of that one, as the longer leg of the left-hand triangle is to the longer leg of the right-hand triangle. But rather than think that every time, I'm going to use this sketch. And then it's easy enough. We got y times y going to give us y squared equals 4 times 12, which is going to be 48. We'll take a square root of both sides and get to work with radicals for a while, for the next longest while. Do you know anything about the square root of 48? Well, it's a little bit less than 7, because the square root of 49 would be 7. Yeah, but let's reduce that radical. 48 is 16 times 3. I say that's important because I know the square root of 16. So it would become 4 times the square root of 3. That's what my length BD would have been. 4 root 3, we'll call it often. And then I got another length I got to go for. I have not yet found out about Z. And I might ask you, is Z a geometric mean? Does one of these sketches indicate that it is? The first one, second, or third one? As a matter of fact, it would be the second sketch. This segment with 2 bars is the geometric mean. Shows up twice in that proportion between its part of the hypotenuse and the full hypotenuse. All right, a proportion. Z is the geometric mean between its part of the hypotenuse, 12, and the full hypotenuse, which is 16. Let's work on that and figure out that length Z, which is also known as BC. We work this out, we'll know the length of BC. Z times Z going to be Z squared, happily. And 12 times 16 is 192. Let's take the square root of both sides. Z squared, the square root of Z squared is just Z. And what about the square root of 192? Well, it is 16 times 12. And somebody could have said, well, if it's 16 times 12, I know the square root of 16 is just going to be 4 times the square root of 12. But that 12 is also 4 times 3. And I know the square root of that 4, it comes out of the radical, becomes a 2, multiplies with that 4, gives me 8 square roots of 3. But probably a clever kid like yourself was saying, hey, that's really 64 times 3, isn't it? And I know the square root of 64. It comes out, becomes an 8. I don't know the square root of 3, about 1.732, but we don't have but an approximation of that, so we'll leave that aside the radical. So, yep, we got 8 square roots of 3 for the length that is BC. 8 root 3. I would be silly to think that you understand all this stuff right now. I'm going to show you some more questions. I just found an old quiz. We'll get you guys to take a quiz kind of like this coming up, I figure. And here I'm going to find A, B, and C, and this is just like the last problem we did. I'm going to go through it fairly quickly. I'm going to find the length that's labeled as A. This is a geometric mean, huh? Between its part of the hypotenuse and the whole hypotenuse. Maybe you want to keep that sketch handy, but isn't this length the geometric mean between its part of the hypotenuse and the whole hypotenuse? So that tells me that A is the geometric mean between 4 and the whole hypotenuse is 14, huh? 4 and 14. If we cross multiply there, A squared is equal to 4 times 14 is, I think that's 56. Take a square root of both sides. Now what about that 56? Isn't it 4 times 14? Yeah, we can think about it that way. And I know the square root of 4 is just 2, so that'd be 2 square roots of 14. That's what A would have been. How about B? And you got to be thinking, well, I know if these proportions exist, is B a geometric mean? And clearly it is, like from this picture. B is a geometric mean. Who's the geometric mean between? The vertical segment in the middle is the geometric mean between the two parts of the hypotenuse, so between 4 and 10. Once we got the proportion, it's pretty easy. B times B going to be B squared. And 4 times 10 is 40. Take a square root of both sides. I know the square root of B squared is going to be B, and that is 4 times 10. I do know the square root of 4, so 2 root 10. That's what the length of B would have been. 2 times the square root of 10. That radical's reduced in good shape. Let's do something sort of like that one more time. Is C a geometric mean? And in fact it is. This sketch indicates that this segment with 2 bars is a geometric mean between its part and the full hypotenuse. So in our case here, C is a geometric mean between its part of the hypotenuse 10 and the full hypotenuse 14. I cross multiply there and I got C squared is equal to 140. Take a square root of both sides and kind of start thinking, can I break down that 140? It's 2 times 70, and 70 is 2 times 35, so that must be 4 times 35. 35 is just 7 times 5, but I don't know the square root of those, so I think I'll leave it like that. But I could call this 2 times the square root of 35. Here comes another. This is more interesting. What could I go for first? This is kind of friendly in that I could get segment P first. But who's the geometric mean that I could use? 3 square roots of 3 is a geometric mean. I'll put it in both of the means positions. Who is this vertical segment a geometric mean between? And you'd have to say between the 2 parts of the hypotenuse. That's coming from this sketch right there, huh? So, the vertical segment's the geometric mean between the 2 parts of the hypotenuse between P and 9. Then you cross multiply, and 9P is equal to how do you multiply these? Outside guy with outside guy? Make a little about that. That'll be 9 square roots of, and inside guy with inside guy is just square root of 9. So I got 9P is equal to 9 times the square root of 9, which is just 9 times 3, which is 27. Divide both sides by 9, and P is equal to 3. I think we need some practice for that, but this length would have been a 3. Now that I got these 2 bottom lengths, these 2 lengths will come quickly and easily. Is Q a geometric mean? Why, yes it is. Who's at the geometric mean between Q? Well, this segment is the geometric mean between its part of the hypotenuse 3. Look at those sketches, and the full hypotenuse 12. This is going to come up kind of pretty. Q squared equals 36. Take the square root of both sides. I'm convinced that Q is equal to 6. How about R? Is R a geometric mean? In fact, it is. I'll put it in both of the means positions. Who's R a geometric mean between its part of the hypotenuse 9 and the full hypotenuse, which is 12, isn't it? Alright, so cross multiply, see what happens. We got R times R going to be R squared. And 9 times 12 is 108. Take the square root of both sides, turn off this video, reduce that radical. But I'm thinking, man, 9 goes into it, doesn't it? But also 4 goes into it, because 4 goes into 12, so 4 goes into it, and 9 goes into it. Probably 36 goes into this guy, doesn't it? In fact, that's 36 times 3. Looking for the biggest radical if I can reduce this biggest perfect square so I can reduce that radical. It is 36 times 3, and I know the square root of 36, so it becomes 6. That comes out of the radical. I do not know the square root of 3. I'll leave it inside. So I got R is equal to 6 root 3. I'm going to go ahead and do these next couple. It's probably good for you to see them. Make this sketch, see what you think. Shut down that video, see what you can come up with. I'm given this length to be 5, and this length to be 6. I'm going to find out about X, Y, and Z. I think this guy was friendly and said we could get X first. What proportion could you write, mister? If I tried to get z as a geometric mean, z would be a geometric mean between 5 and 5 plus x. I got two variables in there. Y is a geometric mean between the two parts of the hypotenuse. So y is a geometric mean between 5 and x. I got two variables in that one also. But what about this 6? Put it in the means positions. And I'm going to requires that you remember this sketch right there. 6 is a geometric mean between who and what? Between its part of the hypotenuse, x, and the full hypotenuse, x plus 5. Oh my goodness, look what we got here. Let's cross multiply. X times x plus 5 will give me x squared plus 5x equals, cross multiplying this way, 36. Now, I know what you're thinking is that, all right, take care of this quadratic. Let's drag it all to one side. I got x squared plus 5x minus 36 equals 0. Got to factor it, huh? Factors of x squared got to be x and x. Factors of 36, I guess it could be 12 and 3. But with that 5 in the middle, it's probably going to be 9 and 4, huh? I got to arrange it so when I multiply those, I get a negative 36, but that middle term is positive. So I think I've got to go plus on the 9 and minus on the 4. If you multiply those, I think you get a positive 5x in the middle. So x is either equal to negative 9 if I set these equal to 0, or x is equal to 4. Since we're talking about lengths here, I'm going to go with x equal to 4. Okay, so this length has to be 4. And it's all downhill now. But that was kind of nice what we just had to do. What about, could you get y? I figured you could if you worked at it. Let's get the value that's shown to be y. You'd have to remember these sketches, or some way to think about these similar triangles. This vertical segment in the middle is the geometric mean between the two parts of the hypotenuse. Y is that vertical segment in the middle. It's the geometric mean between the two segments of the hypotenuse between 5 and 20. I guess I better cross multiply, see what happens. And y squared is equal to 100. Oh, I've seen this question before. Take the square root of both sides. And y is equal to 10. So this length had to be 10. Let me look at that for a second. 5. Y is the geometric mean between 5 and 4. What were you thinking, mister? Between 5 and 4. My mistake, what was I thinking? So y squared is equal to 20. I was thinking that can't be bigger than the hypotenuse. What a dumb thing that I do here. I'll fix it right away. I apologize. Take the square root of both sides, and y is equal to, since that's 4 times 5, I'm going to say 2 square roots of 5. Yeah, that's what that length had to be. I lost my grip for a second there. That's 2 root 5. That's what y had to have been. Now, I did something crazy here. The vertical segment's the geometric mean between the two parts of the hypotenuse, as this sketch would show. Let me do that again. Can I get the value that's labeled as z? Sure I can. Z is also a geometric mean. Between who and what? Between its part of the hypotenuse 5 and the full hypotenuse 9. So z squared equals 45. Let's take a square root of both sides. Square root of z squared just going to be z. What can you do with that 45? Well, it is 9 times 5. And I know the square root of 9. So z will be 3 times the square root of 5. Let's play one more time. This is probably a pretty good one. Let's see what we can do. Who can you get first? Did you get A or B or C or what? And A is the player, huh? I can get A first. 4 is the geometric mean that I would employ. Different things happen different times, but I know if I work with this 4. 4 is this vertical segment in the middle. Is the geometric mean between the two parts of the hypotenuse, between 3 and A. So I got this proportion. And that makes me think that 3A is equal to 16. I got to divide both sides by 3. And 16 divided by 3, well, that's like 5 1/3, huh? That's what this length would have been, is 5 1/3. Not loving it, but that's what we get. How about B? Let's see what happens with B. This is kind of touchy. You can see this was an old quiz, so I'm thinking this is kind of what you would have to expect. B is a geometric mean between its part of the hypotenuse and the full hypotenuse. That'd be between 3 and 5 1/3. I'm going to have to cross multiply and get going on that, but let me get a look at that first, see how I can make that happen best. B times B is going to be B squared. What about when you multiply 3 times 5 1/3? That'll really be 3 over 1 times, let's make this an improper fraction so we can do that multiplication. 5 times 3 is 15 plus 1 is 16, and that's 16 over 3, isn't it? So when we multiply 3 times 5 1/3, it's really multiplying 3 times 16 thirds, which is, since the 3's cancel each other, just 16. So when I cross multiply here, I really got B squared is equal to 16. Take a square root of both sides, and B is equal to 4. That length would have been 4. I'm bothered by that, though. Hold on a second. Maybe you see what I did that was sort of silly right there, and so far into this video. I set up the geometric mean between 3 and 5 1/3. This vertical segment is the geometric mean between 3 and 5 1/3. So yeah, I got 4, because that vertical segment is 4. But who is B a geometric mean between? And I'm sorry that I made that error. This was an error. But you know, you're going to make mistakes also. Catch mine. Who is this a geometric mean between? This is a geometric mean between its part of the hypotenuse 3 and the full hypotenuse. And the full hypotenuse is 8 1/3. This is also going to work out nicely, but I needed to get that right. B times B going to be B squared. And 3 times 8 1/3 would be 3 over 1 times, this will make that an improper fraction. 8 times 3 is 24 plus 1 is 25 thirds. When you multiply those, you just get B squared is equal to, the 3's are going to cancel, just 25, huh? So B is equal to 5. There we go. This length should have been 5. Now, do I get C? Let's do one more thing and we'll get C. Is C a geometric mean? Yes, it is. This segment is the geometric mean between its part of the hypotenuse, 5 1/3, and the full hypotenuse, 8 1/3. Let's work on that for a second. C times C will be C squared. Now I got to multiply 5 1/3 times 8 1/3. Let's make them improper fractions so we can multiply them. 5 times 3, 15 plus 1 is 16 thirds. That's the same as 5 1/3, and 8 times 3 is 24 plus 1 is 25 thirds. This is going to work out nicely. So when I cross multiply those, I'm really multiplying those. And I got C squared is equal to 16 times 25, multiplying straight across the top, is 400. And straight across the bottom, 3 times 3 is 9. Hey, let's take a square root of both sides. When you take the square root of a fraction, you take the square root of the numerator over the square root of the denominator. And the square root of 400 is 20, and the square root of 9 is 3. So it turns out that C, this length, had to be 20 thirds, or 6 2/3. C is 6 2/3. Now, I did make a mistake a little while ago. I screwed this one up. So you be careful. And you see that you could make a mistake too. But I'm going to give you an assignment.